I start section 9.1 here, let me just write the chapter title. So chapter 9 is entitled what? Infinite Series. Infinite series. And I remember as a student, I did not pay close enough attention to this. Infinite series, infinite sequences. They're different. The title of the chapter is this, Infinite Series. But if you want to understand infinite series, you first need to have a solid understanding of infinite sequences. Some pre-calculus classes spend a long time on sequences of numbers, and some don't. So in my mind, it's an important section. Let me point out right now what the difference between these two words is. I mean, obviously, both of these things are going to be infinite, so we'll get to that in a minute. But when I say a sequence of numbers, my favorite example, I think, would be 1, 2, 3, 4, right? There's a sequence of numbers. And if I want to make it infinite, how about I just write this? Is that okay? Dot, dot, dot. When you see the word series, which is what this chapter is about, this means we are adding up the terms and anyone that bowls knows that equals 10, right? Bless you. Now, when I say infinite series, what does that mean I'm going to do? Yeah, I'm going to add up an infinite number of things. Can you do that? If they're very small, can you do it? Can you add up an infinite number of things? I mean, wouldn't the answer be infinity? Or approach something. Okay, now there's the idea, right? Is that, if you remember, I showed you guys the picture of the peanut butter and jelly sandwich. I said, yeah, you want to remember that. You can have an infinite sum that, as Garrick says, approaches something. That's exactly what we're going to mean when we talk about an infinite series, is that we're going to talk about a limit. So let's give you some examples here. Infinite sequences. So when I denote an infinite sequence, I'm going to do it the following way. I'm going to write a variable, and I'm going to put a little letter down here, a subscript, and our book uses N quite often. Some books use I or J also. So the way I'm going to read this, I'll say A sub N. And this is, and I'm going to put braces, which is set notation, okay? So, and the set is going to tell me what sequence I'm talking about. So if I say A sub N is the sequence 2n squared plus 1 over 3n squared minus n, natural numbers in for the n. And so the very first thing I would get, if I put a 1 in for the n, so I'll do this. I'll write here, a sub 1, which is what I get if I put a 1 in for the n. So what would that be? 3 halves, right? Because you get 2 plus 1 is 3, and 3 minus 1 is 2, you get 3 halves. You guys follow that? Some books start with 0. Is 0 a natural number or not? Some books say yes, some books say no. I guess here we wouldn't want to start with 0, right? That's a good point. My daughter told me, she learned in social studies just 2 weeks ago, that the Mayans invented the number 0. Say that there are some small tribal groups that don't have a number for 0 yet. That's true. Some languages they don't have they say 1, 2, and many, and that's their numbers. That's all they need. So it's very, very interesting to study. I recorded all that? That's ridiculous. Here, let me pause this while you guys, could you guys please fill out maybe the next 2 or 3 values of this sequence? Yeah, so I guess what I should say here is that little n is an element of, and you'll see this in math books sometimes. They'll write a big letter with like a double bar here telling you what set we're talking about, and that n stands for what are called the natural numbers, which, as I was taught, start with 1. Okay, those are the Yep, that's what I got, and I got 33/34. Okay, if you can go that far, we're at many for sure. Okay, so let's write another sequence down. Let's write b sub n is this sequence, so I could do 3n cubed plus 1 over 2n squared plus n. And I could do the same thing, but I'm not going to, because I don't want to waste your time. And let me write down c sub n, which is going to be an important example for us. It's the sequence 1 over n, right? So what's that? 1, 1/2, 1/3. Well, I want to start off with c sub n. What can I say about it? Anything? It's what? Decreasing. That's a nice word. This is an example of a decreasing, right? As a matter of fact, when you say decreasing, I guess what you mean is it's always decreasing, right? Always decreasing. There's a nice math word for that, by the way, that we're going to use today. It's called monotonic. So that's a vocab word I guess we need. Monotonic means always decreasing or always increasing, either one. Convergent. Does that make sense to people? C sub n is convergent? Why? It approaches 0. It's convergent. Okay. So how about these other two sequences, A sub n and B sub n? Are they convergent? Or the opposite would be divergent? You think A sub n converges to 2/3? Why do you think that? Okay, what do you mean set n equal to infinity? I don't know what that means. Set it to something really big, like 1,000, right? We could compute. I get 2,000,001. That's not going to change things much. Over what? 3 million, yeah, minus 1,000. So 2 million over 3 million is 2/3. I mean, I agree with you that we're going to be close to 2/3, right? And you are correct that this sequence converges to 2/3. We did that kind of stuff, I think, in Calc 1. We studied rational functions. We talked about the limits. And back then, we were studying the graphs a lot of times. But, of course, when you did Calc 1, you didn't have n's here. What did you have here? You had, like, f of x is 2x squared plus 1 over 3x squared minus x, right? You had the function. And we talked about asymptotic behavior. Okay. How about bound? So we could write this, or we could say it diverges. Right. Okay. So some of the same ideas you had in Calc 1 come back here, I think. I want to point out just briefly that this whole idea of converging or diverging is very tricky. So in the 1800s, famous mathematician that I'm going to bet you may not have seen his name. Have you guys seen this one yet? Cool. I'm introducing you to Cauchy. If you continue to take math courses, his name will show up probably in every one of them. That's what I think. To continue along the lines of math courses. Cauchy in the 1800s that Euclid is credited with introducing rigor to what math subject? Nope. Geometry, right? He took he actually wrote a geometry book that is still used today, translations of it. And in the United States, it was used as recently as 30 years ago. You guys did Euclid? Right. On physics? Okay. So, anyways, some people think Cauchy did that for mathematics. But there's flaws, too, that he had. He had a problem with his definition of limit. And he was a great mathematician. Here's his definition of limit. I'll read it to you. Brought it in. He said, when successive values of a variable approach indefinitely to a fixed value in such a way as finally to differ from it by as small a quantity as is of words that you may wonder what they actually mean. Indefinitely. I mean, I guess that's the ... up there. approach indefinitely. What does that really mean? Can you be more precise? And nowadays we can. And if you take a course called Analysis someday, which some of you will, especially you math major people, what you'll do is you'll take a course where we prove the stuff in calculus. I love that intro to it, but that's what it is. But this is not an analysis course, so I'm not going to go crazy, okay? We're going to introduce you to these theorems. Today, you're going to see this section has theorem after theorem after theorem after theorem. We'll see how this all works.